Okay, great. Let's get started today. So just one announcement. Tonight there's going to be a class poll that's released, which is just sort of an informal way that's distinct from the end of class feedback for us to get feedback midway about what you think about the course, the pace, the workload, and things like that. So it'd be really great if you could fill that out, because it's helpful to the professors. And then just a side note, so I took out some content that was in the course the last time I did it, which was an entire lecture on the proof that SGD converges to its global maximum under certain conditions. And some of the staff told me that they really loved that lecture. And so for those of you who may love that lecture, I posted it, but you are not responsible for it. If you really want like a really rigorous hour-and-a-half long lecture's worth proof, it's there for you. Okay, who's gonna look at it? Who's gonna make a drinking game out of it? Okay. Right, so where were we? We've been talking about classification and about, in particular, most recently about the discriminative versus generative kind of classification, and we got really deeply into Gaussian discriminant analysis, which was a generative model despite its name. And so just to refresh your memory, what was the intuition with these generative models of how we make a prediction for a classification prediction? So we basically, for each class, this is this analogy of the lion and the elephant, you basically have a template. It's not just feature-based, but you actually kind of have some memory of what each class looks like. And for Gaussians, it's a particular Gaussian with, say, a particular mean and a particular covariance. And then you essentially, using that template, you compute the probability under that template for each of the classes, and then you renormalize it. So that's kind of the intuition of how you make a classification prediction for these generative models. And so, as we saw, we went through all these different things where what if the covariances are tied to be the same? What if they are spherical? What if they're arbitrary? And how does that change the implied decision boundary that we get? And so even when we let everything be decoupled and arbitrary, so in particular we let the means be different, we let the covariances be different, and we let the covariances have any arbitrary structure, the most we got was a quadratic set of decision boundaries, right? So that's actually not very complicated somehow. And so could we get something more complex? And I think someone asked a question last class that was like a nice segue into that, and I believe I even said this last class, is one way you can make it more complex is if for each class you allowed it to be a mixture of Gaussians. And then you could get, if you allowed the mixture to get as large as possible, then you could have essentially an arbitrary decision boundary. So that kind of takes us into clustering a little bit. So it's a bit of a segue. So far we've been doing all this supervised stuff. And now we're going to talk about, oh, I think I put that slide in the wrong place. All right. Right, okay, let's scrap that. We're not yet into clustering. We're still talking about decision boundaries. And so I was saying you could have a mixture of Gaussians, but you could, in general, not even have Gaussians there, right? Like you could put anything arbitrary there that you can do computations with. And so in general, we're going to put some sort of density model there, which means a probability over X. And when we condition it on the class, we call this like a conditional density model. And so a Gaussian is, of course, one example of a density model. And PCA is actually also a density model. And it happens to be, if you look at probabilistic PCA, so I don't know in what detail, if you looked at that at all, but it turns out there's a probabilistic version of PCA, which is one of these, what we call these latent variable models. We'll talk a little bit more about these still. And it's also a generative model, and it turns out that that's a density over X, which happens to have a low rank component in the covariance matrix, plus typically, well, in PCA, also a diagonal. So that's just another example. We're not going to go into that any more than you. Did you guys see that probabilistic PCA in the first half? Who thinks you did? Who thinks you didn't? Okay, I guess you did. Right, so we could take any density model and then just have a different one for each class to get this conditional density model, and then we could throw that into this framework of generative classification models. So, so in the discriminative model, only y is a random variable, right? And in the generative model for classification, we said both of them are. And so, but we didn't talk about this distinction for regression, right? So I only brought this up with classification. But does it remind you of something you saw in regression space? Can you guys think of like an analogy that you did see in the first half of the class? Either shout it out or raise your hand. I can't hear. So when we did linear regression, that was probability of y conditioned on x, right? So that's the analog here of a discriminative model. Did we do any regression models where we had both y and x as random variables? Right, total least squares. So it's kind of a similar idea, but generally people talk about this discriminative versus generative in the classification space. I don't think I've heard it in the regression space, although I don't quite know why. That's just how it's evolved. And just to emphasize though, in any case, even if your only random variable is y, you can always generate y as conditioned on x's. And so again, just to remember that the terminology can be quite confusing, and it's just these are the conventions. Okay, this is where it's supposed to say introduction to clustering. Okay, so that's where we are. And so that was all about supervised, where the labels were classes. And so now the idea is, what if we had kind of a similar setup, but we didn't know the labels, right? So in clustering, you may have, I don't know, has anyone seen this in another class? I actually don't know what gets taught nowadays in college. A few people. Okay, cool, not very many people. So the idea here is that we don't have labels. So it's not a classification problem. No one has told us the labels. All we have are examples of x's and no corresponding y. So this is analogous to PCA, right? PCA, you don't have labels either. And so what we want to do, unlike in PCA, where we're trying to find a kind of more compact, low-rank representation of the data, here we want to assign labels to the points that somehow nicely that are somehow informative. And so an example here an algorithm might say all of these points get one label, the blue label, and the other ones get a red. And the idea is that the clustering algorithm is going to infer these labels in a way that optimizes some objective function, if we're lucky. And so this is what's called clustering, starting with a bunch of unlabeled data with no classes, no labels, no regression label, and then putting them into two different classes, or more than two, some number of classes, k classes. So more formally, the task is, given data x, we want to infer discrete and unordered class labels, if you will. They're not really class, well, I guess they are class labels, but we don't know them ahead of time. And based on somehow the structure of how they lie in the input space. So by structure, what I mean is, if it was just two-dimensional and the points actually plotted like this is a pretty obvious structure, right? So you and I could just go by hand and say, these should be blue and these should be red. But this is a trivial example to do that. Like one can manually do it here because one, it's only 2 dimensions, and the data happen to have this really nice unique cluster that makes it obvious. But in general, it's actually a really hard problem that you couldn't possibly do by eye. And so, right, one of the most unsupervised, so this is a type of unsupervised learning, and again, as you've seen, one PCA is another one, but that's different because you're not assigning these discrete labels. And so you can also think of clustering as reducing the dimensionality to 1 in a way, right? Or because in this case, all these data points get the same label and all these other ones get the same label. So after the clustering algorithm has finished, in some sense, that's a summary of the data, as these guys get a label of 1 and these guys get a label of 2 or blue and red, whatever. Again, they don't have an order. And sometimes, before you cluster, you might actually want to apply dimensionality reduction. So, for example, in the next slide I'll show you. So this is actually from like a real paper in Nature Communications. It's not an area I work in, but some other people here at Cal do. And so in this case, this is very high dimensional data, which is single cell immune data. So for a bunch of individual cells, which they've only been able to do this kind of technology in the last, I don't know, 5, maybe 10 years, and you can go in and measure expression of like 20,000 genes. So in principle, these X vectors are no longer 2-dimensional, they're like 20,000 dimension. But then you can actually do dimensionality reduction down to say 2, and then you can cluster in that 2-dimensional space. And so that's one example of how it gets used. And actually exploratory data visualization in like the sciences is a really big use case of this. Is you measure, you spend millions of dollars and a year of graduate student time getting these data, and then you want to have some idea of what it means. And so very, very frequently people will do things like clustering to get a sense of like, well, how many different cell types were there and things like this. So another reason you might use clustering is you might be trying to infer a number of latent subpopulations. So maybe you just have this group of cells and you're pretty sure that there are some distinct kinds in there, but you don't know what they are, or you don't even know how many there are. Or maybe you have some sort of marketing data and you want to break it down into categories to then go do some further analysis, but you don't know what they are a priori. So maybe you cluster your data, and then from the results of the clustering, you go downstream and do some more. And sometimes you just use it as pre-processing to make it more compact before supervised training, or add that label in as a feature, sort of different twists you could do. And also kind of interestingly, there's something called Outlier Detection, which we won't go into in this course, but it can be used for a number of reasons. And so in this example, like a lot of these examples you see that are visual are kind of toy examples, although that last one from the paper is not. But in this case, imagine you have these sort of 2 clusters and you want to know what the outliers are, which are like these black points here. And so if you have these clusters, then you can also have some way of saying, does this point belong to which of these clusters or to none of these clusters? Okay, so what are the sort of formal things we want to have a clustering algorithm do? So there's 2 kind of really obvious ones. If you haven't seen it before, not obvious, but when I tell you, I think you'll agree they're obvious. So one is that we want the distances between points that are within a cluster to be as small as possible. And that means that, like, because they're supposed to be a summary of the data that they all got this label red, so they should somehow all be similar, so they should somehow all lie closely together. And then the other thing we want is to have large distances between the clusters, because the idea is that they should somehow be different from each other. And if they're completely overlapping, then we lose that intuition. And so, and when you read about clustering, or you hear people talking about it, you'll hear these, sometimes they'll talk about similarity, sometimes they'll talk about distance, and in some sense, this is also in the eye of the beholder, right? Like, how do I measure these things, and is it a Euclidean distance, what kind of distance? And that's gonna be kind of like choosing the kernel when you're doing kernel ridge regression, or kind of like, which in turn is similar to which features do I pick? Like, do I do polynomial featurization, or do I do something else? You're gonna have the same kind of game here, is like, how am I gonna measure similarity in the space? And many other questions as well. Okay, I think I just said that. And the difference, though, here is when you're doing ridge regression, you can try different kernels, or if you're trying different features, just like polynomial features, you can do cross-validation and you can see which one works best, right? You have like some holdout set, and then you try a couple of different things, and the one that works better is the one that you anticipate will work better if you do your cross-validation properly. But here we don't really have any way to evaluate it like that, and that's why in some sense it is kind of exploratory. You can't like prove to someone that this is optimal unless you make a whole bunch of firm assumptions. Right, and so what just technically, distance is the same thing as a metric, and formally it requires all 4 of these properties. So if D is a distance, then if J and K are the same, the distance better be 0. If J and K are different, the distance better be greater than 0. It should be symmetric, so if I swap the order of J and K, I should get the same distance. And that's why this KL divergence we brought up last class is not symmetric. And then finally, it also needs to obey the triangle inequality. And dissimilarity is almost the same. It's not quite as stringent. You don't need to have the triangle inequality. You just need to have the first 3. And then actually similarity is just the complement of dissimilarity. Okay. So now we're going to go, and I'm going to sort of slowly, like for the rest of the lecture, I'm going to kind of get you deeper and deeper into a particular viewpoint of clustering. First, I'm going to just talk about centroid-based clustering as a general concept here, just for like a moment, and then I'm going to tell you about a particular version of centroid-based clustering called k-means, and then we're going to kind of think through what's going on in k-means and maybe what's not ideal about it, and then work our way to what is a more rigorous approach to clustering than these. So this is sort of a slow build-up of intuition and how to think about the problem. So in centroid-based clustering, each cluster is represented by a point in the same space that the training data themselves lie in, but the centroid need not be one of the training points. In some algorithms that we're not going to look at, you might constrain it to be that for various reasons, but here, just anything in that space. So if this were the clustering, C1 maybe is somehow the center of this defined, but defining center in some way. And so k-means is the most common of these centroid-based approaches. So in the centroid, in k-means, and generally in centroids, the entire kind of model, if you will, is defined just by these centroids, ck. And again, these are just, it's like a point in the same space that the data lie in. And so the parameter fitting is to find the best set of these centroids. And so then you say, okay, well, what is best? And that's going to be like a question one should think about deeply. And in fact, there's not a clean answer, so we're just going to kind of teach you how one can think about this and what some of the conventions are. And also it is kind of in the eye of the beholder. So we've mentioned 2 criteria so far, right? This intercluster and intracluster distances as things that we might seek to minimize and maximize. And it turns out that the k-means algorithm, it says that the best centroids are the set of centroids such that the distance of each point to its assigned centroid is minimized. So in other words, if all these red points are assigned to this centroid, then that centroid better be the one that for which the distance to all of them is minimized, perhaps the Euclidean distance. And in fact, that's what we're going to, the running example here will just be Euclidean distance. And so it's actually only optimizing the intra-cluster distances, right? There's nothing in what I just said, which is the flip side of that, of maximizing the inter-cluster distances. Okay, so formally, we have these training data. I can see already a typo, because D is apparently the dimension, and it's here. Okay, I'll need to fix that. So just ignore this D. So you have a bunch of training data, endpoints, no labels in D dimensions. And a cluster partition is going to be essentially, each of these is a set which contains those points that is assigned to that cluster. So if a point is in cluster 1, it belongs to this set. And the union, this is a partition because there's the points can only belong to one cluster. And then there are k clusters. Does that make sense? Okay, great. So for example, x3 belongs to cluster 2, it's going to appear in this guy. And so, right, and again, each of the k centroids lives in the same space as the data points. And we want to fit the parameters. And so the objective function, I just said it in English before, but we can now just write it down, which is that we want to find the centroids, which are the parameters of the model, but in order to find those, we also need to find the partition. So we need to find the partition of the data points where they're assigned to each cluster, and the centroids such that this whole thing is minimized. Okay, so I just rewrote it here on this slide. So how are we going to do this? So this isn't maximum. This is not MLE, right? Because I don't have a probabilistic model here. And it is discrete optimization because I need to find this partition. So as soon as I'm finding a partition, that's discrete optimization because I'm basically putting these things in this bin and these things, other things in that bin. And it's also a linear optimization because given a partition, it's a, well, actually, is it linear? Actually, I'm not sure. Let me think about that. Okay, but in any case, the question is, if you knew either the parameters or the partition, would that somehow help you, like, to solve this? So let's think about it in one direction, and then we can think about the other. If we knew the one, what would it be like to solve the other, and then vice versa. So suppose that we knew the partition. So we knew which points were assigned to which cluster. So in other words, these were red, these were black, these were purple. Then how could we find the centroids? So I think it's actually pretty easy because the optimization would just decompose by cluster because these points are assigned only to this centroid and these only to this centroid. And so it just reduces to the centroid is the thing that satisfies this. So only the points for that cluster and the other points disappear, and you just do this once for each cluster. And so we know actually that the answer to that is just the mean for this. So that's actually, so if we knew the partition, it'd be super, super easy to get the centroids. Okay, what about the other way around? Suppose we knew the centroids, then how could we find the partition? The optimization would amount to assigning each training data point to one of the k clusters. And so there's a kind of obvious choice here, which is to just choose the cluster which is closest according to that objective. And so if you do that, you just say Zi is going to be the one that's closest, then you get a partition which says it's all the x's who have their Zi computed like this equal to k. So it's really just, if you're closest to the centroid, then you get assigned to that partition. Okay, so that's pretty simple. So we can put this all together, and it turns out this gives us an iterative algorithm where it goes back and forth. So the first thing we do is we have to initialize somehow, because what I told you is assume we know one, and then do the other. But at the beginning, we don't know anything, of course. So we can initialize with either of those steps, but typically people would initialize the cluster centers somehow at random. And in various ways, so if you have k clusters, maybe you just pick k data points at random, and you could get, the more clever you get, the better the outcome, probably. And then you just repeat this until convergence. So you have the centroids, and we just explained how, given the centroids, you can compute a partition, and now given a partition, then we compute the centroids, and we just go back and forth. So does this converge? Who thinks this converges? Who thinks it doesn't converge? Okay, can someone explain why it converges? Yeah, so at each step, it basically, it can only reduce it or stay the same, right? So if I've got the centroids fixed and I repartition it, I'm repartitioning it in a way that it has to go down kind of trivially, and similarly for the second step. So it does converge. And if it doesn't change, then we've converged. But we, of course, only have a local minimum. And so this is actually a very, essentially an NP hard problem. And at best, we can run multiple restarts to get to different solutions and then take the best one of them. Okay, so this is just a little animation of how this might play out. So now we have some data points with no labels. And then we assign each point to the cluster. In this case, so it's not starting with by initializing the centroids, it's starting by initializing the assignment of the points to one of three, blue, purple, red centroids. And then given that initial assignment, now it computes the centroids. So you can see this red is kind of in the middle of the red points that were assigned at random, similarly the black, and similarly the purple. given those centroids, now we repartition the data. And so you'll see that as I advance the slides, it's going to kind of clean itself up, right? So the little things are getting closer to where we think they should be. And you can see here, though, right now, at the moment, this is half black and half purple. It's kind of partly purple and partly red. And as it keeps going, just advance it, and then you get more black, it's going to keep going. And then actually you saw, this started bleeding in red down here, but that's going to go away. And then there we go. So this is like kind of a nice, perfect example. It doesn't always work so perfectly, of course, but I think it gives you an idea of, even when you just randomly initialize and you have nonsense at the beginning, that it still does something quite sensible. Okay, so could we have used gradient descent here? That was like a cute little algorithm that makes a lot of sense. Who thinks we could use gradient descent? Who thinks we can? Okay, good stuff. Right, so we would have to take the gradient with respect to the partitions, and which are discrete objects, and so we can't do that. So basically, we can't, but we can actually. So there's a paper in which this is written. I think it's not actually very commonly known. So you can rewrite this loss here to not be a function of the partition. And what you do is you replace the partition with a min function, effectively. So here, instead of looking through all x that belong to ck, here you just, for a given point, you get only the relevant centroid by applying the min operator. And so now the thing that wasn't differentiable, which is a partition, is gone. So min is is actually mostly differentiable, and so you can actually just say let Ri be the closest centroid to k. So in other words, it's the solution of this minimization. And then if you do that and you take the gradient, you actually do get a gradient that has an indicator function here, depending on whether Ri is equal to k or not. So if you're, for a given point, you only affect the gradient if you were closest to that centroid. And so I actually don't know, I don't think people use this, but it's kind of neat to think about it. I think it's a good exercise to always ask yourself these questions of like, well, could I have just done the things I know about? What would go wrong? And things like this. And so it turns out you can do this, and it actually does converge. But the standard algorithm for k-means is the one I just described to you before with the cute animation. But this is going to have a sort of analog later on in the lecture when we get to a more rigorous model. It's going to turn out that you can do something that's a lot like this alternating k-means, but actually it's going to be rigorous, and you can alternatively do gradient descent. So, okay, how would you pick k in k-means? So there are different ways, but loosely speaking, or like quickly, you could do something similar to PCA where you pick the elbow in, say, the mean squared error curves. And so, because of course, as you add more and more clusters, the loss is just going to go down. So you can't actually use sort of a cross-validation procedure. You can use specialized cross-validation procedures that most people don't know about, but typically you would just look for how the loss changes, and you look for a kink. You'd sort of say, well, it went down a huge amount from 1 to 2, went down a huge amount when I added a third cluster, and then after that, it looked like it didn't really help, like maybe that's just in the noise. Okay, so this is a pretty simple algorithm. I don't remember when it was invented, but it is actually used a lot of places. So these are just some examples here. So what this actually is yeast genes, where each colored line here is from one yeast experiment, and then you get measurements of each gene, which is just over time. And people sometimes want to understand, like, are there certain collections of genes that behave similarly? So you may, if you've taken biology, notice that there's like a cell cycle related to like the reproduction of the cell. And so maybe genes that are kind of all related to cell cycle will cluster together and things like this. So it can be actually quite interesting to apply something like k-means, which they've done here, and group together genes and ask one, just which genes ended up together is by itself interesting. And secondly, then you can also say, well, what does their pattern look like? And that might also be interesting. So these are like the centroids corresponding to each of these clusters. Okay, so here's an example of, I actually don't know how many clusters here, k, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, I don't know, maybe there's something like 64 clusters here. And so, right, so this is actually the best of performing k-means over 10 random initializations. Can you guys spot any weird errors?
Orange. Orange.
Bottom left orange, yeah. So that like looks like this should all be one cluster, but the boundaries are putting it into two different ones. And similarly over here, and then also over, for example, like here, these are all in one cluster, but they kind of look like they should be in two clusters. Similarly here. Okay, so some of the obvious clusters get broken up, and some of the obvious distinct clusters get grouped. This is not perfect. So are these definitely errors? I think it's tempting to look at these cute plots in a pedagogical exercise and say, yeah, those are wrong. But as I said before, like no, like it's kind of in the eye of the beholder. It's mostly just exploratory, and you can't, without a lot more information, say whether that's right or wrong. I mean, I suppose you could, if you actually knew the labels ahead of time and you pretended you didn't have them, and then you clustered, then you could say, okay, well, then it was right or wrong. But this, if you had that kind of data, you would never perform clustering. So. And so that makes it quite, again, distinct from regression and classification and other supervised methods. Right, and so, so in some sense it's kind of weird. I'm saying you can't evaluate it, and yet these things are actually very practically useful in a huge number of applications and domains. Okay, so more about what are some of the things we might desire from clustering. So I said there were these two things. Can anyone think of any others? Mm-hmm. An efficient number of clusters? Yeah. You want, yeah, so that's right. That's a good point, and that's not in my list. So, right, you would want to get the right number of clusters, whatever that means. And that's usually, that choice is usually auxiliary to the clustering algorithm. So, unless you go to very advanced algorithms, you always give it a k, and then you say for that k, run it. So it would be nice, but generally we're not going to be able to get that. Anything else? Okay. So one example might be that we want to have invariances to rotation or scaling of x. So imagine that I just applied a rotation matrix to x. Should the algorithm give me back the same clustering? Well, who knows? That depends on what you want it to do, but you could imagine that you would want this property. I mean, it's not an implausible property, right? And similarly, scaling, like, should it be that if I just scale all my data by 10, like, should the algorithm give me something totally different? That might be kind of crazy, right? So these are very plausible. And so if you want things like these kinds of invariances, rotation and scale invariance, is there some way we can guarantee these? If the clustering algorithm is driven entirely by the distance or similarity, then as long as that distance or similarity has these invariance properties, then so too will the clustering. And so that's one way to think about it. And this should remind you a little bit also of like kernelizing. When you take an algorithm and you put everything kind of in the kernel, then a lot of the properties arise from the properties of that kernel. Okay, so this is, you probably don't get this in most introduction to ML class, but actually I remember this when I was a first-year graduate student at Navy. I know, it was before I was in grad school, and I went to what's now called NeurIPS, and when it had already existed for decades, but I guess maybe you guys might not even have been born then, I don't know. And I went to go talk to him at his poster, and I've always loved this theorem, so it's pretty cool. So he says there's 3 clustering goals, of which provably you can only get 2 at a time. I'm not going to prove it to you here, but it's still interesting to think about. So one is scale invariance. So if I stretch out the data, in other words, I take the distance and multiply by c, then clustering should stay the same. And that seems like perhaps something you would want. Another one is consistency. So if I stretch data such that the distance within a cluster only gets smaller, and the distance between clusters only gets bigger, then the clustering algorithm should also give me the same results. And the third one is richness, which is that the clustering function or algorithm should be able to produce any arbitrary partition of the data points. And so he proves in this paper that actually you can only get 2 out of these 3, which is, I think, kind of cute. All right, so, but aside from that, let's go back to k-means. Can you think of any weaknesses with this algorithm as it's been presented so far? Yep. They're just circles, yeah. Why are they circles? So how could you get it not to be a circle? Right, so right now each xi is treated the same. So if you kind of reweighted, which implicitly means it's somehow like a spherical loss, right? And if you weighted each feature differently, then you could get a kind of different shape, and that might very well make sense. So yeah, that's one of the ones. I can't advance because then you'll see that's not my first one. So that's somewhere there. But okay, the one I have, because I'm obsessed with probabilistic models, because I just think they make the most sense, is it's not a probabilistic model. There's no likelihood, and that makes it really hard to understand these assumptions. And so actually, you made a really nice point, is you made a comment about like it's spherical, and so, but if we actually had somehow introduced the language of probability and Gaussians here, like we could actually just look at it directly and not have to think in these kind of strange ways. It would be just generally probabilistic models, you're being really upfront about your assumptions. And as was just said, is this also implicitly corresponds to clusters with sort of a spherical shape because each feature is treated equally. And then the other thing is that in each step, the optimization is sort of like has this hardness to it because it's a combinatorial optimization problem. And so it might be nice to somehow soften that and not say like, I need to pick the thing that's best, but maybe like I can sort of spread it out and say, well, I'm kind of along this much in that cluster, this much in that cluster. And that might be helpful for optimization. It might also be helpful for interpretation, right? So, well, who's to say that each point should actually just belong to one cluster? Or that we have enough information to judge that is the other reason. So we can kind of now tweak k-means to like, and so when I guess generally in computer science when we say hard or soft, like hard means like usually like a 0-1 decision, and soft means somehow relaxing that to lie in between. And so with soft k-means, rather than having a hard assignment to a centroid, we're going to soften it up instead. So right, can you think of how we might do that? Using ideas from the previous lecture, or 2 previous lectures? I don't know, it's a blur for me. What's that? Logistics, something about logistic, yeah. So we can basically pipe those distances through like a softmax, and then now we'll get, instead of a hard max, we get a softmax, because we use softmax. And so I can take these distances, and this is just putting it through softmax. And so now instead of getting 0, 1, I hard belong to one cluster, I actually get a distribution of how much I belong to each cluster. And so this sort of relaxes that last point there. And I can actually augment this also by putting a beta in there. And similarly to logistic regression, the larger the beta, the sort of more peaky this distribution will be. Sort of somehow it'll be more confident in where it is. And technically, it has a lower entropy, and we'll talk about entropy in a little bit. Okay, so now that we're thinking about it this way, where we don't take a hard assignment, but if we go back and think about what the algorithm was doing, right? It was going back and forth between this was effectively the hard assignment. It said each point goes to one partition, and then we computed the centers and went back and forth. So in light of the fact that soft k-means we're not going to have a hard partition, can you think about how we could adapt this iterative scheme to make use of it? So maybe just take like a minute to see if you can think of how to do that. It's a good exercise. Who thinks they have an answer? Okay, so let's go through. So we're going to replace what before was this hard assignment with a soft assignment. So I kind of already told you that. And then, so that basically takes the place of the partitioning, right? It is actually just that step. Don't partition, instead do a soft assignment. And then the question is, how do I use that soft assignment to update the new centroids? So before, I just took all the points that belong to centroid K and I just computed their mean, right? Like this. But now I can't do that because there's not some fixed set of points. Instead, I have to basically include each point kind of proportional to how much we believe it's in there, according to, so this number is a softmax, remember, is a probability. It's between 0 and 1. So if it is a 0, then it shouldn't appear at all. And to the extent if it's a 1, it should fully appear. And if it's somewhere in between, then it should only kind of get a partial vote on where the centroid is, right? And so you can show that now the centroid update should look like this. So it's just kind of the same as the mean, except you weight it by how much you believe that point belongs in that cluster, and then when you do that, you have to renormalize by those as well. So it's almost the same update, but you now get this blending of points from everywhere potentially to affect the centroid to different degrees. And so also, again, this is like a good tool for you just to think about as you go through things like this, is to say, well, what happens if these actually were only 0, 1? I know in softmax that they lie between 0 and 1, but if they are only 0, 1, then actually this just collapses to this. And so that's kind of reassuring. Okay, so what are the unanswered issues with this soft k-means? Anybody have concerns or things like, how does this work? How does that work? So like maybe how should we set that beta? I said the beta sort of affects something about the distribution we get for the softmax, but I didn't say how to set it. And we're still treating all the features in xi equally, so the spherical assumption is still there. And it might actually not make sense. So maybe in some cases, I mean, you can even just imagine in some of those toy examples I gave you, some of those look like circles, but if they look like they were elongated, then you would want not to use a circle. But we don't really know how, right? Like, so we can sort of hack at this because it's sort of a ad hoc method in a way, even though it converges. And so we made some progress. We sort of softened things up. We said we could add this beta, and we've gotten some flexibility. We started to think about it, but we can probably do better. And so for me, better is usually going to a probabilistic model. And so that brings us to something called a mixture of Gaussians, which is a formal probabilistic model. And then we're gonna, once we understand what the model is, then we're gonna ask about how we can fit its parameters to do maximum likelihood estimation. And we're gonna, in the course of doing that, introduce a new optimization algorithm that's very specific to these kinds of models, and as we'll see, called expectation maximization. Okay, so mixture of Gaussians, and I mentioned this before, these is just kind of, you have a bunch of Gaussians all together that make up the density. And so you might see this visualized in different ways. Does this look like chocolate? It makes me hungry. But these are like the contour lines. Like this is probably the most formal one, where this is one feature, this is the other, and these are the level sets of the density. Once, I guess it must be 3 Gaussians here, some of them are elongated, right? They're not all spherical. So each cluster is now represented, so each cluster is now represented by a Gaussian, kind of like in the LDA and QDA stuff. And we're going to end up with similar model consideration. So when we were going through the generative models called Gaussian discriminant analysis, we were saying, should the covariance matrices be spherical? Should they be tied together? And all these things. And we're going to have the same considerations there. Basically, do we want these Gaussians like to somehow share information like covariance? Do we want them to be any arbitrary shape or not? And so, now I'm going to say take a minute to try to write down the likelihood for one data point, given that there are k Gaussians, and that you don't know which of those k Gaussians it belongs to. So that's why it's different from from the Gaussian discriminant analysis. There we had a label, right? And here I'm saying write down the likelihood for a point when you know that it's a mixture of k Gaussians, but you don't know which one it came from. if you haven't seen this, it's probably hard, but I feel like it's just good to think about it a bit and to get stuck and then to see the answer. So I'll give you like a hint, which is we're going to let Zi be a hard assignment to cluster Zi, but we don't know it. And that's why we call these latent variables. And so we have to marginalize over it. So we have this variable Z, which is the hard assignment, but we don't know it. So we have to kind of sum it out, right? So how are we going to do that? We're going to take the joint density over these and then just sum out Z, and that gives us the marginal. I mean, that is just the operation of marginalization, the definition of it. So that's actually pretty straightforward. And then we can just plug in how we want to do the modeling here, which again is going to look a lot like the LDA and QDA. So we're going to break up the joint of X and Z just using the rules of conditional probability to X conditioned on Z times the probability of Z. And then each of these is going to be, again, similar to the Gaussian discriminant analysis. It's a Gaussian also, and so each class has its own mean and covariance matrix in general. And then you have a probability of each of the labels. But in contrast to those models we learned before, we don't have any observations of what, like, we don't have those labels. We're just positing that there was one, and we don't know it for any of the data points. And so that's the big difference. It looks really similar, but it's actually fundamentally different. And often when people write these, they'll call this last thing here alpha k, sort of the prior probability that a point belongs to any cluster. And then, of course, these have to sum to 1 because you have to belong to one of the clusters. So the parameters that we want to learn in this likelihood are going to be the means and the covariances and these things that we call mixing weights, which is like kind of how much of each cluster we think there should be. And there should be one of these for each k. Okay, so this is this idea of a latent variable, which I don't think you've seen much of in the class so far. And so just a little aside on these. So sometimes we intentionally introduce these it's kind of weird, right? Like I introduced a variable for something that we never observed. So why did I do that? I introduced this random variable for which we have no realizations, and then I essentially integrated it out or marginalized it out, right? And so for the mixture Gaussian, I introduced this Zi variable, which denotes the cluster label of the point xi. That's a typo, not just which of the k clusters it belongs to. And so these latent variable models, sometimes we use these because they let us define a very complex set of dependencies between observed variables, but in a way that's really intuitive, right? And without having to characterize some crazy dependencies. So in this mixture Gaussian, just by virtue of introducing this Z thing, I could like kind of very cleanly explain to you that I believe each of these points came from a Gaussian. I just don't know which one. And so if you didn't introduce that, it would be much harder to think about these models and to write them down. So somehow this kind of simplifies it. Aside, there's another, lots of typos today. Okay, that should say aside too, but maybe it will aid you. So the latent variables kind of make things a bit more modular, and sometimes people refer to them as a way to sort of kind of like Lego blocks. You can divide and conquer the problem by putting little pieces together, because conditioned on one of these things, then sometimes you get like nice pieces, like a Gaussian, you get a nice Gaussian out of it. Right, and sometimes people think of them as a way to place sort of an expert in different parts of the space. And these are sort of different examples where you, like in this case, there's 3 Gaussians, and you can think of this Gaussian as an expert for these points, these are an expert for these points, and things like this. Sorry, there's a little glitch. I need to go clean these up. Okay, but so the other thing that's going to be interesting, and we'll get to that, is that the struct just go to this point. I think I just repeated these, right? Yeah. Oh no, I see. I was trying to be fancy and I confused myself. Okay, good. This is the last point, which is that when you have these latent variables and it introduces this kind of structure, it's what's going to lend itself to some specialized optimization algorithm called expectation maximization. And so we're going to make our way there. So, right, so as we said, the likelihood for one data point under a mixture of Gaussian density is the P of xi is given by this, which we just went through before. And so over all data points, I just multiply them out, this thing. And then typically we deal with the log. So the log likelihood now looks like this. And so this is a bit different than we usually see, because normally when we take the sum over the log of the probabilities, we don't have another sum in there, right? So this is distinctly different from what you've seen because there's a sum that's inside the log. And that's because we had to marginalize out this hidden variable or this latent variable that we never saw. That's where it comes from. And that's going to turn out to kind of make things a bit messy. Because if you take the derivative now with respect to things, it has to go through a log, and this couples everything together in a way that we haven't seen typically before for models that look a lot like this. So you could try to write out the derivative and see that it's quite messy. So okay, so that's where we are. But so nevertheless, we could actually just treat this as any other objective function, and we could just do gradient descent like we've seen, and that actually would be fine. But there's another. As I've said several times, there's another thing we can do, which is to take advantage of the structure to make things easier. And this is what's going to produce the expectation maximization algorithm. This is like a somewhat complicated algorithm, but it's really prevalent, and it's also the building blocks for more complicated things in machine learning beyond the scope of this course. And so it's one of the fundamentals, and it's good to have some idea of what it is. So let's try and do that. So right, expectation maximization is a parameter estimation algorithm. It's specifically useful when the parameters are tied together via a log, kind of like we get, almost always it arises with these latent variable models. And it does exact maximum likelihood estimation. So somehow people often get confused and think it's some approximation. It's actually doing exact maximum likelihood estimation, and we're gonna actually prove that. So, and so one thing to note is when you have problems that look like this, it's going to be kind of similar intuitively to what we saw happening in k-means, which is if we knew the values of this zi, if we knew which cluster each point belonged to, then the likelihood would be like really nice, right? Instead of having that second sum, it would go away because you would only do it for the relevant cluster. I guess there's some notation missing here. It should just be for the cluster that xi belongs to. Okay, so in light of that, we're going to get something that looks a lot like k-means, but is actually like sort of derived from probabilistic principles and is provably equivalent to, or it provably is doing maximum likelihood estimation. But before we go into all the technical details, I want to give you some of the intuition. And so the intuition is that we're going to initialize with random cluster assignments. And so which is essentially the posterior of that latent variable given the data. That's going to be sort of the soft assignment. It's very, very similar to soft k-means. That's why I sort of slowly went through this to get to this point. So these are these sort of soft assignments, but it's cast as a true probability. It's the probability that it belongs to, I should actually have a k in there. So I apologize, I'll go clean these up after. It's weird, I thought I had completely cleaned them up. Right, and that's going to kind of, in some sense, fill in these missing variables. So we're going to compute the probability that it belongs to each cluster given the data and the current parameters. And then, given that we've kind of filled in this missing data, we're going to do maximum likelihood estimation on this, what's now kind of quote unquote fully observed, where it's going to, again, it's going to look a lot like soft k-means, where the parameters get updated by a blend of points, each of which get different votes depending on their posterior probability. And so, right, this looks a lot like k-means, only now we have a principled loss function, which is a likelihood. And so so when we have parameters that kind of play the role of beta, or we want to change the shape and things like this, it's going to emerge very naturally because we're going to put those constraints or those lack of constraints in the covariance matrix and things like this, and then we'll just do maximum likelihood estimation. So there's no more sort of fiddling about with k-means to soft k-means to putting the beta in or not, and things like this. And so, right, we're going to show that this procedure that I described up here, and I'm going to kind of go through it a few times to try to get it into your head, is exactly doing maximum likelihood estimation. And it's a general technique, so it's not specific to the mixture of Gaussians. And sometimes I find out that people learned it in this context and they think it's just for mixture of Gaussians. In fact, I know like famous professors at famous institutions who've told me this, and I say, no, this is a very general algorithm. It's just that gets taught with mixture of Gaussians often. Okay, so first I'm actually just going to tell you the algorithm because it's going to look a lot like k-means, and then again I'm going to slowly bring you to the more technical and general viewpoint of this algorithm. So right, we've seen this before. This is the same thing with the log we don't like, and we're going to use these alpha k's, which are the probabilities. Which are right there. Let's see it. Okay, just that's the probability that belongs to each cluster a priori. And so we're going to get these two steps that are going to be kind of like the two steps in k-means. So in the first step, we're going to, and it's also going to look a bit like the Gaussian discriminant analysis. It's going to be like kind of a weird combination of everything you've seen in the past couple of lectures, but this is kind of like, what we do is we're going to say, it's like a score for the nth data point and how well it scores for the kth cluster or the kth Gaussian. This is kind of actually like QDA, right? Also, like this could be like the lion template or the elephant template, and what's its score under that. And then to get the posterior for each cluster, I have to normalize. And so this is actually really, really similar to GDA. So Gaussian discriminant analysis, right? So I basically get a score for that point belonging to each cluster, and then I normalize. And inside of the normalization, I include this prior probability. And so now these Q's are the posterior probability that point n belongs to the kth cluster. And if I sum over all these QKNs for a given data point over all k clusters, it has to sum to 1 because it's a probability. And so, and then what I'm going to do is, given that I've done this E step, so that's, again, that's sort of like the partitioning or the soft partitioning with the softmax. Right, this isn't a softmax, but it looks very similar. Then I'm going to do the M step, and this is, so the E steps is for the expectation part. And then the M step is to do the parameter estimate. So this is sort of like updating the centroids. And we have 3 parameters. We have a mean, we have a covariance, and we have these, what we call these mixing proportions. And it's gonna, again, it's gonna look a lot like soft means, where I'm gonna get, instead of just the average of points assigned to a particular centroid, and now the centroid is actually a Gaussian that has a mean and a covariance. So this, before we just kind of had the means, right? Like these were the centroids, and now I have this covariance, which allows me to make it spherical and all kinds of things. And so I'm gonna compute the mean of those points weighted by how much I believe each point belongs to that Gaussian. And so right now I'm giving you like a recipe because I'm trying to give you the intuition, I'm trying to link it to the previous thing, but we are going to actually, I'm going to show you how to derive these updates as well. And I believe you have to do this in one of your homeworks. And so the covariance matrix is actually, so this actually, if you look at this, this is nothing more than the maximum likelihood, like estimate of a Gaussian mean, except the points are weighted. And here, this is similarly, this is the maximum likelihood estimate of a covariance, except it's weighted, each point gets weighted by the Q, again, by how much we think it belongs to that, that Gaussian. And then to figure out the overall probability that any point should belong to the kth cluster, we just sum up basically like average how much each point belonged to that cluster. And then this will normalize to 1. So that's the intuition. Does that make sense? Like it makes sense. We started with like regular k-means, then we went to soft k-means for some reasons, and we said, yeah, this is a bit wacky. Like let's go to a coherent, like rigorous probabilistic model. And then I told you there exists some algorithm. I didn't tell you how to derive it, but I just told it to you, and it's kind of very similar. Do you guys at least get the intuition of what's going on here? Okay, so could you go program it after this class? Who thinks they could? Okay, who thinks they would have trouble? Can someone tell me why you would have trouble, or it's like, is this so crazy you don't even know? I'm sorry? What is the data? Oh, theta. Oh, sorry, theta are the parameters. all the parameters together, whatever relevant ones you need. Yeah, that's just a placeholder for theta. But yeah, I should fix that too. Does that help? Now can you code it? I'm trying to understand like where, like if I could explain something better or other. Yep.
So the data x is raised to the power 10.
Okay, that's also, sorry, I was too lazy to type this all out and I took some screenshots from somewhere. This is just the nth data point.
Oh.
Yeah, there's no power raising. Okay, all right, these are good questions that probably should have had preemptively explained. Any others, yeah?
Can you go over what the Q and the P's are represented again?
Yeah, right. So P is kind of like the analog of, it's just saying for the nth data point, how much do I believe it belongs to the kth cluster by evaluating its density under the kth cluster Gaussian. So it's sort of like a score. It just says, I'm going to do this for each, like for one data point, I'm going to compute it under Gaussian 1, under Gaussian 2, under Gaussian 3, and I'll have 3 different numbers. And the more it belongs to one of these, the higher its sort of density will be, right? But then what I want is I want a posterior probability. Like this isn't going to give me a probability between 0 and 1. It's just an arbitrary density. So what I want is I want to know the probability that it belongs to cluster 1, Gaussian 1, probability that it belongs to cluster Gaussian 2, and so forth. And to do that, I mean, you can go through the, I haven't put all the steps here, but you end up basically just normalizing those things, and it looks like this. So I have skipped some steps here. Does that help? Okay.
So Q sub n is the probability that point n belongs to cluster X.
Yeah, so it's the probability of z given that you've seen the corresponding x. Like you've seen the nth data point, you have some value of the parameters, and you've evaluated, and so it depends on these, right? So you run this for each k for that data point, and then you basically this is like a renormalization such that it sums to, if it's between 0 and 1. Yep. Yeah. J. Where is there a J? I see. Should it be J and yes, it should. And look at that. Yep. Good call. All right. So okay. So it turns out that most of the confusion is from really sloppy notation. All right. Anything else? Yeah. The z is this notion of this latent variable we introduced, and this is like the nth one. So for n data points, this is the nth z. So for the nth data point for xn, the nth data point, it has a corresponding latent variable zn, and that is the value of the cluster it belongs to, except we don't know it. So we just introduced this thing which we would like to know. And so instead of knowing it exactly, we're going to compute probability that it was equal to 1, to 2, to 3, to 4. Some more questions, yeah?
What would be the initial value of y?
So as with all these algorithms, you have to just initialize them somehow, and you can kind of do it at random. You can try to get clever. But so with EM, you'll have to, you either initialize what you would use in the E step, or similarly to k-means. In k-means, I said you could either initialize the partition, and then given that partition, you compute centroids, or I said, and in the diagram I showed you, you could, that's the way it worked, but you could have instead initialize the centroids, and given those centroids, then that. So here, I could either initialize these QIs, which is equivalent to saying, for each point, I'm going to just tell you how much you belong to each cluster. I could do that at random, or I could go to the M step, and instead of that, I could just say this is going to be the mean, this is going to be the covariance, and this is this, like at random or through some ad hoc heuristic procedure. And as long as you need to either give it a first E step or a first M step, and then you're going to iterate between these after that. Any other questions? Yep. So which one? No, it's literally the evaluation of this thing. So it's just the evaluation of the xn in this of a data point, of the nth data point under the Gaussian, the kth Gaussian. It's just literally the value of this. Yep.
Can you explain how we update alpha?
Yeah. So right here, I haven't, like, I will go through and show you how you can drive it. So right now I was just trying to give you a sense of what, like, when you turn the crank of actually deriving EM for a given model, wanted to give you a sense of the intuitive updates that emerge and how they're kind of similar to soft means. I haven't derived these here. I'm just kind of giving them to you, and I'm trying to get you to understand them at an intuitive level, because EM is actually a remarkably intuitive level, even though it's sort of technically quite deep. And so, right, I didn't derive this, but and we'll see how you can drive it. But the update is that for the kth cluster, this is just the probability that it's sort of the prior probability that any point belongs to the kth cluster. And what you're going to do is you're going to take the amount that for each data point, how much it believes it belongs to that k thing, and then you're just going to average them. So for example, if all the data points had been assigned a probability of 1 to cluster 3, then this would add up to n, and n divided by n would be 1, and the probability that they belong to cluster 3 would just be 1. If only half the data points had that, then this would end up being a half. And of course, in general, Q lies between 0 and 1, and so these alphas will always lie between 0 and 1, but they will always sum up to 1, which isn't necessarily obvious from this, but it will be later. Any other questions? Yep?
What does Z represent
Intuitively, there's this, like, so we have these data X, and when we do clustering, when we decide to do clustering, in our head, we think each point belongs to one of k clusters, but I don't know what it is. So Z represents that thing we want to know. It represents, so for each data point X has its own Z. And that Z is the cluster it belongs to, which of course we don't know. And during this algorithm, we're going to get the probability that Z equals 1, probability that Z equals 2, probability that Z all the way up to k. Okay. Any more? I guess this is a one way to fix typos. All right, so now you can all go and code it because you have no more questions. Great. Okay, so right, this feels a lot like soft k-means, where we get the soft assignments from computing these kind of scores, which get converted into normalized probabilities. And then given those, like just with k-means, we use these to update the Gaussian mean and the covariances. So again, it's like really, really similar, but it's like it's coming from a sort of correct probabilistic interpretation. And so we can actually, even though I just told this to you, like it's not obvious that this is any better at the moment, right? I showed you a proper probabilistic model, and then I skipped a whole bunch of stuff and said, trust me, this does maximum likelihood estimation, but we can prove that, and so that's actually what we're going to do. So I'm going to start in on this, and then I'll finish it next class. This will maybe, yeah, and I'll recap some of this. So let's just start a little bit in on this. So the likelihood, again, has this form. So each data point I, and then I have to marginalize out this thing Zi that was just saying is this, I don't know which cluster it belongs to. So to get the probability of X, I have to sum over all possibilities that it might belong to. And that's how I get the likelihood in these latent variable models. That's just a property of marginalization. And so it's going to turn out to be, we're now going to start just introducing some concepts that are going to be useful for the proof that this is equal to maximum likelihood estimation. And so one thing that we're going to introduce is something called the complete log likelihood. And a lot of these have very intuitive meaning to them. So the complete log likelihood basically looks a lot like the likelihood, except I get to, I don't have to marginalize out Z. I pretend that I know essentially what cluster it's with. And that's going to make it a lot easier. It's going to be like a very workable object somehow. And so that's the complete, and it's complete because I've sort of augmented it with this information that's missing, which is the clustering label. So that's why we call it complete, because I'm sort of just pretending that I have that complete information even when I don't. And then I'm going to need something called the expected complete log likelihood, which is the expectation of this under some arbitrary distribution Q. So I'm just taking this thing that I introduced, and I know right now, I know you don't know why I've introduced it, but we're gonna slowly get there. And the expectation of this is called the expected complete log likelihood. And so we can just write that expectation as a sum where we move the q over to here for some distribution q. And we want to leave it general for the moment. So these are just sort of setting up some notations and concepts. Okay, so it's going to turn out that the expected complete log likelihood is a lower bound to the likelihood, and we can go through a series of steps. So again, this is now, I'm just going to do it for one data point, but it sort of generalizes. So that one data point, probability of xi, given the parameters of the mixture of Gaussians, all of them theta, is again, we're just going to marginalize out the z. So we already saw this. This is when I said take a minute to write out the likelihood. This is just the same thing. And now I'm going to do a bit of a sleight of hand. So this you haven't yet seen. I'm going to multiply and divide by the same thing, which is some arbitrary distribution q. So that's all I've done, is I'm multiplying and dividing by the same distribution. So I'm allowed to do that. It's going to turn out to be useful. Okay. And so that, I can also rewrite that. You can always go back and forth an expectation and a sum by basically pulling, I can pull out this guy and make it into the expectation distribution here. So this q becomes the expectation distribution, which leaves me with these two things, which appear down here. So this is just going between writing an expectation with an e and writing it as a sum over the variable of interest. Okay, so now this is where, this is sort of the crux of EM and of other things like variational inference that we won't have time to go into. But so what you do is, this is where you get a bound on the likelihood. And so you use something called Jensen's inequality. Some people say Jensen's, but that is wrong. Don't do that. You don't have to understand any of this, but if you remember to say Jensen's, you will look smart. Okay, so what this does is Jensen's inequality, and I'll let you sort of ponder this diagram on your own at home, but basically what it says, based on convexity, is that the expectation of a function is always less than or equal than the function of the expectation. And here that expectation, as a toy example, is just showing you 2 points, A and B. So it's basically saying that because for convex functions f, so log is convex, and I want to apply this bound here to this property here, and I'm going to do it because log is convex, and it says that the log of the expectation is going to be greater than or equal to the expectation of the log. And you can actually, it's pretty easy to see pictorially if you think of that expectation just as being over 2 points, A and B. So here, right, so the expectation of f of x, so f of x is at A is here, and f of x at B is here, and the sort of, let's say the average of them, we can think of as the expectation is here, whereas the function of the expected value of A and B, so just here for intuition, think of expectation as like the kind of average of A and B is here, and if I take the function of valuation of that, I'm up here. So this sort of demonstrates intuitively this bound in a simplified example, just to give you some intuition. So nevertheless, I can take the likelihood, which is this marginalization over the thing that I wish I knew, and I get all the way down to this thing, and I'm going to keep going from there. I'm going to now I'm going back and forth between the sum and the way and the expectation way of writing things, and I'll write it. I'm just now putting this q back in and writing it as a sum again. Except the difference from where it is before is that the log is here. So over here, the log was outside. And now I got the log inside, and that's going to turn out to be really nice for us. It's not obvious yet. Right now, I know it's just like a bunch of weird garbled math, but this is how it goes. Okay, and then finally, I can write that out. I can break it up into 2 terms. One is going to be minus. I'm going to put a minus here because I want to pull this q up to the numerator of the log. So minus the q log q. And then the other term is going to be a q log p, which is this here. And these are actually the entropy of this q distribution. I haven't told you what the q distribution is yet. I just said it's some arbitrary distribution. And then this is actually this object, the expected complete log likelihood. And so what this says is the likelihood is essentially bounded by this. This thing is always less than or equal to the likelihood. And so we're gonna kind of, let's see, I'm just trying to see what's on the next slide and see if it's worth wrapping up right now or going for another 5 minutes. Well, okay, let's keep going, and maybe I'll revisit some of this and with more correct notation and review some of the questions we had today. So this whole long thing is to say that I can write the likelihood in a way that I bound it by these two terms. And that's gonna be useful. So we now have this lower bound on the log likelihood, which is this likelihood is always greater than or equal to the entropy of this arbitrary Q distribution, and this thing I called the expected complete log likelihood. And so just as an aside, if you haven't seen entropy, because I'm using it over here, this entropy thing, so we've talked about the decay, the pullback Leibler divergence, things like this, so I don't think we formally introduced this, but the entropy of a distribution like this is just the summing over all the x's, the probability of x times log p of x. This also comes from information theory, has some interpretation in terms of bits and things like this. There's a continuous analog, and it basically, when you see it appear in machine learning, you typically, and I guess everywhere, you want to think of it as some amount of disorder in a system. So we say that like a distribution is entropic, means that it's very disordered, so like a flat distribution is very entropic, and the more peaked, right, and then this has minimal entropy if it's very peaked. And so the less the information is concentrated, then the higher the entropy. And as you get to like a delta function, this has like the least amount of entropy because all the information is concentrated in one place. So, right, so that's this entropy term here, is it has something to do with this distribution, Q, that I haven't yet said. So the idea is that somehow I'm going to use this bound on the likelihood to actually derive this maximum likelihood estimates for expectation maximization. But I feel like maybe this is enough for one lecture, so I'm going to actually clean up the slides, and then next time I'm going to go through, hopefully with cleaned up notation, see if there are any more questions, and then get to the end of this group. So, okay, thanks.